Alright, so in this example problem, we're going to assume that the circuit is hooked up to a 100-volt power supply. So between here and here, we're going to have 100 volts. And we're going to find the equivalent capacitance, the charge on each capacitor, and the potential across each capacitor. Alright, so this one's a little bit more of a complex system. I come in here, I split into two legs. So this rung and this rung are going to be in parallel each other, but these two are in series. So I need to combine these in series, and then that equivalent will be in parallel with what I've labeled as capacitor 3 here. And then this entire equivalent capacitor is going to be in series with capacitor 4. So let's step in through and do that. So the first thing I need to do is do the 2 and the 4. So we're going to do 1 over the equivalent capacitance is equal to 1 over 4 plus 1 over 2 because they're in series. So my equivalent is going to be 1.33 microfarads, which is why I've labeled this down here. So the 1.33 and the 10 are in parallel with each other. So I'm going to add those together. So 1.33 plus 10 is 11.33 microfarads. And then I've drawn what the circuit equivalently looks like at this point in time. So the 11.33 and the 5 are in series. So I'm going to do the 1 over the equivalent capacitance is equal to 1 over 11.33 microfarads plus 1 over 5 microfarads to get 3.47 microfarads. So that's the equivalent capacitance of this setup of capacitors. Alright, so now I want to find the charge and the potential across each individual capacitor. So when I go from my equivalent capacitance of the circuit and I step back one, they're in series, which means I can use the voltage from the power supply and the equivalent capacitance to find the charge that flows from here back to here. So I'm going to take the 3.47 microfarads times 100 volts, and I get a charge of 347 microcoulombs. So that's going to flow from here across here. And since this is an actual capacitor, that is the charge across capacitor 4. And I can use the capacitance equals Q over V again with the 5 microfarads and the 347 microcoulombs. They get 69.4 volts. So capacitor 4 up here is taken care of. But this 11.33 microfarads is an equivalent capacitor. So I'm going to step back and I see that they're in parallel with each other. So the charge, the 347 microcoulombs, is going to split in between the two legs, but they're going to have the same potential. So I'm going to use that 347 microcoulombs in the equivalent capacitance to find the potential that applies to both of those capacitors in parallel to each other. So 11.3 microfarads equals 347 microcoulombs divided by volts. That's 30.6 volts. And since the 10 microfarads is an actual capacitor, I can take 10 microfarads times 30.6 volts, and that gives me a charge of 306 microcoulombs. So capacitor 3 is handled. But the 1.33 microfarads is an equivalent capacitor, so I have to step back again. And that's a 4 and a 2 in series. Since they're in series, they're going to have the same charge. So I'm going to use my equivalent capacitance to find the charge. So I'm going to take my 1.3 microfarads times 30.6 volts because we know through this leg there's going to be 30.6 volts. But there's going to be so much dropped across this capacitor and so much dropped against this capacitor. This means that I get a charge of 40.7 microcoulombs, and that applies to both because they're in series. And then I can use the individual capacitance, so 2 equals 40.7 microcoulombs divided by volts. My voltage ends up to be 20 volts. And then whenever I do the 4 microcoulombs equals 40.7 microcoulombs divided by the voltage is going to equal 10.2. So now we have the charge and the voltage for each individual capacitor. And what's kind of neat is you can go back through and double check your work, because even though the voltage against these is going to be different because they're in series, they need to sum up to whatever potential is flowing against the 10 microfarad. So the 10 microfarad, which I labeled 3, is 30.6. So we expect this plus this to be pretty close to 30.6 based upon a little bit of rounding. and you can see that it is. And even though these two are in parallel, the charge that comes from here and splits between the two of them, it needs to add together. So when this charge with this charge has to equal what's flowing through here. So if we check that out, that would be what was flowing over the 10 microfarad, so 306, and what's flowing over this equivalent, so I used the 1.33 here, so that would be 40.7. So when I add that together, I get pretty close to 347. So you can go back through and check your work to make sure that even though they're supposed to be different, they still have to add up to either, and when they're series, the charge needs to add up to whatever is coming into that junction, or if they're a set in series that's in parallel with another one, these voltages have to add together to equal the same voltage as this.